The last logarithmic model that we're going to look at is pH. So pH is a measure of the acidity of a substance. And those of you in chemistry who are in chemistry, maybe you've come across this scale already. So pH typically ranges from 0 to 14, with acids ranging from 0 to 7. So this area up here is acidic, and bases are going to be from 7 to 14, with 7 being neutral. If we take a look at the formula up here, we'll see that the pH is given as negative log of this thing here, which means it's the concentration. This H plus down here is a concentration of hydrogen ions in a substance, and it's measured in moles per liter. So the more hydrogen ions in a substance, the smaller pH, right? It'll be more acidic up here. And notice that this graph or this function is reflected in the x-axis for the logarithmic function. So because of that, the more hydrogen ions, the smaller the pH, and the more acidic the solution. Okay, so we're going to do two examples. In the first example, we're going to find the hydrogen ion concentration, so this H plus, for a solution in which the pH is 5.8. So we're given the pH, we're asked to find the hydrogen ion concentration. So pH is given by negative log of the hydrogen ion concentration. In this problem, the pH is 5.8, and that's equal to negative log of the hydrogen ion concentration. First thing we want to do is isolate the log part of this function. So I would multiply everything by -1 or divide by -1, whichever one you want to think about it. And we'll get negative 5.8 equals the log of the hydrogen ion concentration. To undo the log, we can exponentiate both sides or simply rewrite this in exponential form. So we get 10 to the negative 5.8 equals the hydrogen ion concentration. And if you punch 10 to the negative 5.8 in your calculator, you will get 1.58 times 10 to the negative 6, and the units are moles per liter. In the last example, we're going to do the problem in reverse, and we are going to figure out what happens if we decrease the pH by 1 unit. And this is similar to what we saw with the Richter scale, the last Richter scale example. Okay, so for purposes of this problem, let's say that we let the pH go from 3 to 2, and we'll compare the hydrogen ion concentration for each one of these. So first, if we have a pH of 3, we'd have 3 is equal to negative log of the hydrogen ion concentration. We would move the negative to the other side. So we'd have negative 3 equals the log of the hydrogen ion concentration. And then to undo this log, we would bring the base to the other side. So base to the other side, so 10 to the negative third equals the hydrogen ion concentration. So if the pH is 3, our hydrogen ion concentration is 10 to the negative third moles per liter. Let's do the same analysis, but now let's have pH equal to 2. And this example, I'll put a heading on it, is pH equal to 3. So when the pH is equal to 2, we'll use our formula or use our model. So 2 is equal to negative log of the hydrogen ion concentration. Bring the negative to the other side, dividing both sides by -1. And then this one I'll exponentiate for those of you who like to exponentiate both sides to undo the log. So we'll get the hydrogen ion concentration in this case is 10 to the negative second. Okay, so how do these two hydrogen ion concentrations compare? Right, so we had one of them was 10 to the negative third, the other one was 10 to the negative second. So we can conclude that as the pH is decreased by 1 unit, the hydrogen ion concentration increases by a factor of 10. And if we were to decrease the pH by 2 units, the hydrogen ion concentration would increase by a factor of 100. If we decreased it by 3 units, it would increase by a factor of 1,000. So this is the same type of thing as the Richter scale because it is, once again, a logarithmic scale with a base of 10.